that for live streaming as well. Welcome to the March edition for the New York HR Analytics meetup. My name is Jeremy Shapiro, and I have the fortune of being the co-host for this event, along with Stella Lutoshore over here for those who have not. And we've been running this for over 10 years. Just as a raise of hands for how many of you, this is the first time you're at one of our meetups. Welcome. That's fantastic. For anyone who's been here, let's say more than 3 times, a bunch of folks as well. Fantastic. So for those that are that this is new for you, the whole goal of this meetup is to informally learn quickly about important topics inside of people analytics. When we started this 10 years ago, it was not this many people. And it's certainly on the web as well. We were not streaming, we were not doing any of that type of thing as well. This is not my day job. I lead the people analytics team at Merck. Before that, I was at Morgan Stanley doing similar things. But this is a growth for all of us together. Things are changing far too quickly, and the only way through it is community, and that's one of the things that we believe deeply as we work through this. Tonight is actually going to be incredibly special because we have so this is not your formal designation, but I'm going to designate you as. I believe that we're going to be hearing from the finest mathematician that thinks about people analytics topics on the planet today, and we're absolutely thrilled to do this. And let me just ask, so how many of you already knew Keith McNulty from Fantastic? How many of you own one of his books? Let's say the book, the handbook for regression and modeling as well. It's sitting on, it's literally on the back of mine. If you've ever seen it on video, it's part of the book that have right there. It is an arm's reach. And I know many people analytics folks that literally, if they have someone new to the function, they just buy your book. That's so I'm going to read just a few bits from your bio, and Keith is going to come up and basically do your thing, because you are fantastic at doing this as well. So, Keith, and I'm going to stare at him as I talk about this is life. So Keith is an applied mathematician and statistician, psychometrician, and data scientist. Now, one of the things that I think is cool is my assignment is the data scientist was you. You made yourself into a data scientist by learning it of everyone else from all the other work that you did. And we got to see that live on LinkedIn. So if you've not already followed Keith, by the end of today, follow him so you can see all the cool stuff that he posts. So for years and years, you were at McKinsey and you were leading the people analytics function at McKinsey. It's one of the times that we got to play together and to talk to each other is some fantastic work that you had done there. You are now at Citadel, which is why we get into New York, because Citadel is partially in New York as well. You're also ranked as a LinkedIn top voice for data science analytics and in AI. You have now 3 books, right? Yes. And one is, I think you updated one just recently as well. They are both in print, which buy the books, support what's going on, but also online. And the online stuff is fantastic because you're constantly updating it as well for new methodology as well. I mean, like from a personal perspective, I kind of feel like what you've done, Keith, is influence so many new talents in analytics to join people analytics today through the postings that you've done. So I want to thank you for all the work that you've done there. And essentially, we're all going to see both online and live a little bit of that sharing, the open sharing that you have across this entire platform. So we all have a great round of applause for Keith.
Thanks so much, Jeremy. I mean, the reason I come here is just to listen to Jeremy speak about me. Look, thank you to everyone who's in person today, and to everyone who's joined online. For the in-person people, I'm sure, some of you probably traveled the distance to come here, and I really appreciate that. For the online people, I'm sure a number of them are joining at quite an unsociable hour from somewhere in the world, so I really appreciate that too. Yeah, I think Jeremy gave you my background, but really, I have to thank Jeremy and Stella and the team here. They organize a really rich group here, which has been running with success for over 10 years now. And that group has added so much value to professionals over the years. And the amount of effort that goes into it shouldn't be ignored, right? I mean, I came here and watched like Stella go through the stress of trying to set up this hybrid setup. But, these are all things that they would notify. So first of all, like, thank you to those guys. Quick round of applause for those guys. And also thank you for giving me a platform here. This is the second time I've spoken to you guys about the same book, really, I think. And it's really helpful for me to be able to get my message out there and also be able to share my materials in this way. A little bit of a story, as Jeremy mentioned, until last year I worked for McKinsey. Like, I finished up with McKinsey in September or so last year, and I had like 4 months free before I started my new job. And I remember, all my friends, my colleagues at the time saying, "What are you going to do with your 4 months? You've got 4 months free." And I think they were, saying I was going to go on various holidays and, relax. And my response was, "I'm going to update my book." And I think they were a bit surprised by that. But I did want the fun stuff as well, so it wasn't just the book. But one of the reasons why I updated the book and actually started to flip on, I'll talk a little bit about the book. The book is, something that, first of all, this would be great. Just hold there, Stella. I'm going to be sharing some content, some technical content, because that's kind of my style in these talks. It might not be easy to see it on the screen, depending on light. So everything that's happening here, you can follow on that link. So I'll give you a second just to pull that up. And that would be permanently up online. And there'll also be a link to the actual, code underlying this as well, if you want to go away and try it yourself. So I can move on to the next one. So thank you. So this is the first edition of the book, which kind of came out in 2021. And I actually remember just over 5 years ago now, doing from my home since the middle of COVID, the last talk for this particular group. And it was just after the first version of the book had launched. And it's been out there now for about 5 years or so. And the purpose of the first version of the book was kind of to educate professionals in the most common explanatory methods that we use in people analytics. And as I said at the time, one of the motivations for that book was everybody was obsessed with predictive analytics at the time. And everybody was like, "I want to learn Python, I want to be able to predict, to do these all amazing algorithms." But in people analytics, most of the questions that we get asked is not like, "I want you to predict something." It's, "Why is something happening?" And any of you who work in HR or people analytics probably know, that if you bring a prediction to your stakeholder, they're not going to trust unless you can explain like what is driving the prediction and why is that happening. And normally they're interested in influencing the process, not predicting the future of the process, right? How do I change my process to get it to work the way I want it to work? So regression modeling is like the best technique out there for doing that type of work. And I felt like it had been forgotten a bit in all amazing algorithms that were being thrown around at the time. So I thought I'd create a book and it would show like all the basic regression techniques that you would need for dealing with people like that. And I was really pleased with how well this book followed and taken on. But of course, when you create a book, you start getting requests for new content and other stuff that people are interested in. So over the years, I started to hear, can we have more on X? Can we have more on Y? And so by the time I got to last year, I thought, okay, now I kind of know here are 2 or 3 things that I could add to the book that would make it even more like rich in content. So as Jeremy says, if you're having it on your shelf, I want to increase the chance that you pull it down, you can find the exact method you're looking for if you're kind of working with data. So in particular, one of the things I left out in the first book was modeling around count data. So things like absentees or safeties, sort of things like that. How do you explain like what also those could increase? I've left that out completely in the first edition, so put in a new chapter on that. And then really what I'm going to focus this talk on is the big assumption I made in my book was people that model tend to have access to at least a few hundred observations when they're doing modeling. But actually, there's a lot of people in their jobs that don't even have that, right? They're working with 20, 30, 50 observations at most. So I wanted to introduce a new paradigm which some of you may have heard of, but it's called Bayesian modeling, right? And it's another way of looking at how we think about likelihood and probability in models. And I want the idea being that for me, like somebody who is really well educated in regression modeling can do it from both angles, right? They can do it from the classical or what we call frequentist way of modeling, which is great if you have good data and lots of observations. But you can also take the Bayesian approach, which is really good if you have smaller data and if you want to like bring expert knowledge into your model more than you can with the other approach. So my goal was I want to be able to educate people to do both. And so there's 3 chapters in there, kind of take all the models that are in the original book and say, here's how you do them slightly different way, particularly if you use small data. And so it makes it quite comprehensive. I think that's the aim of it. So I'll go through some examples and we'll actually have some fun exercises and a fun kind of probability game that we'll play as part of today's session. I've set it up so we can do it hybrid. But if anyone wants to take away, like actually try out the code that I'm using in this presentation, if you're a coder, there's a link within this presentation to code on GitHub. You can just pull it down and use it. But also pretty much everything I do here is in the book itself, which is already online and you can start using the print version. I think I have to submit it by the end of this month, so it'll probably be actually released around Q3 suspecting. Keep it move on. So first of all, it's interesting. When I said I was going to do a talk about small data, everyone said, "What do you mean by small?" Which is quite subjective, right? So small data could be considered data where the number of observations you have or the number of rows of data that you have is less than 100. Where did that come from? Me. Okay? It's no formal definition. It's just by rule of thumb. If you go below 100, you're starting to get into territory where every time you run a model, it tells you something really, really different, and that's not great. So that's the thing, and that's quite common in people analytics, right? So maybe you have a data set that's 1,000, right? And you do a great model on it, you produce the results. But then one of your stakeholders says, I only want to see it for the people we have, or I only want to see it for that department, right? How many people are familiar with that type of, the log cancer going up, right? And sometimes I call that a fishing expedition, right? What I mean by that is sometimes they're asking that question because the original model you produced is not telling them what they wanted to hear. So then they want to filter the data to see if they can find a way of getting their hypothesis confirmed, right? So it's a lot of confirmation bias in that way of thinking. But the reality is that we are like looking at data that can be quite small at times. Sometimes you're working for a small company and it's all you have. Sometimes you're doing experiments on a small number of people, or sometimes you're big enough to filter it down to a particular department. So there's a couple of challenges with trying to use like traditional statistical methods, so kind of things that are in the first edition of my book. The first thing is that when you run larger sample sizes, what you tend to get is the inferences that come out of your model are quite narrow. So you can be fairly certain that your values lie between a couple of points that are quite close together. And that gives you small p-values, which is always nice if you're confirming hypotheses, but it's kind of a nice, comfortable environment to work in, right? But when you get below 100, you start to have problems in my experience. So when we're working with small data, the challenge is ramp up, right? You get a lot more uncertainty. So the idea behind frequentist statistics is you do things repeatedly. And by doing them repeatedly, you get a pattern that helps you have some certainty, right? But the problem is if you do things repeatedly on small data, you often get no pattern or very, very wide pattern. So it's a lot more randomness in small data. The other thing is that if you have small data, then it's natural to think, okay, I just don't have enough data here to be able to make a decision on using the data by itself. I need to somehow mix this with whatever we already know in terms of expert knowledge. And so, by taking the expert knowledge and adding a bit of data to it, I'm probably going to get a better outcome than using the data. So that's, what's another way of thinking about it. So we really need to achieve 3 things when we're working with small data, right? The first one is we need to have some expert knowledge about the process we're modeling, if that's at all possible. We need to have a way of incorporating that expert knowledge into our data. That's a weird concept. How do you incorporate knowledge into a quantitative model? Okay, that's fascinating. the Bayesian approach allows you to do that in a particular way, which I'll kind of go through. The last bit we need is a more precise way of talking about uncertainty, right? So in traditional statistics, you'll like come out with something called confidence interval, right? And that means that basically your value to a 95% confidence is somewhere between these two blocks, right? That can be quite wide. That doesn't tell you a lot. And you can't really do anything more subtle than that for statistics. But in Bayesian statistics, you can actually say, there is a 53% probability that my coefficient is greater than 0, or there is a 62% probability that my coefficient is between these values. So you can be much more precise about probability. And that's really, really important if you're dealing with a greater or more uncertain situation. You can actually say to your stakeholders, instead of like your value is somewhere between this hugely wide range, you can say, I can tell you that there's a 60% chance that your value is greater than 0, right? Which is more helpful. If we can. So let's look at what I mean by that, right? So here's a quick example. So, there's an R package and a Python package underlying my book that contains all the data sets that I use in my book. And here I'm loading in a classic data set that I work with right frequently in the book, right? It's a data set of academic test scores of students that are on a biology degree program. That's a 40-year-long program. And each column is the score that they get in each of the years, year 1, year 2, year 3, final year. And there's a different scale. Like I think year 1 is out of 100, year 2 and year 3 is out of 200, and year 4, the final year is out of 300. So the original data set here is 975 students, right? So by my definition, that's not small data, right? That's a reasonable data to be working with. Now, what happens if we ask ourselves a question like, is second-year test score correlated with final year test score, right? Now, what we typically do is something called a correlation test. The purpose of the correlation test is to test the hypothesis that your correlation is not 0 or is greater than 0 usually. So here, like I'm running a fairly simple piece of code in R where I'm asking it to do a correlation test between year 2 score and the final year score. And I'm asking it to do all of my data, right? 975 observations. And I get the results back here, and it tells me that to 95% confidence, my correlation is somewhere between 0.26 and 0.37. That's a fairly narrow inference. Gives me a lot of assurance to you that there's definitely a non-zero correlation here. And that's then supported by a p-value, an associated p-value, which is extremely small. It's pretty much 0, right? So we are very, very confident on the basis of this correlation test that we're not dealing with a 0 correlation between these two values, right? So that's great. We've got reasonable data. It's giving us narrow inferences. We can very quickly say, that we can reject the null hypothesis. It's a good chip. We're confident that there's positive correlation between these two measures. But what if we only had data on 20 students? Right? What happens then? Thanks. So here what I'm doing, and this is something I do a lot in the later chapters of my book when I start to look at these new modeling techniques, as I say, let's take the same data set, but let's just take a very small slice of that data set and let's pretend that's all we have, right? So here what I'm doing, and for those of you that don't code or have not seen this type of thing before, a lot of code where you're taking random samples, it's always good to put a line in that says, I'm setting a seed here. And the reason you're setting a seed is because although you're doing a random process, one of you might want to take this code later and replay it. And I want to make sure that when you're pulling that sample, it's the same random sample that I put. So by setting your seed, that guarantees that you get the same randomness that I got. And so all I'm doing now is I'm taking the same data set. I'm just taking a random 20 observations, 20 rows from it. I'm working with that as my data set. Now I do the same thing, run a correlation between year 2 and final. Then look at my confidence intervals between minus 0.31 and 0.55, right? So like I'm not able to tell if there's a non-zero correlation here at all. My p-value is 0.52. You can flip a coin. So this is a problem, right? And this is always a problem when we work with small data. You know, these inferences are not natural. It's very difficult to use traditional statistical methods to get like a clear point of view, or at least a point of view that you can articulate effectively to your stakeholders. So we got now I'm talking this p-value, right? Okay, and p-value is like one of the most controversial terms in statistics because it's always very poorly understood exactly what p-value actually means. So I'm going to give a pop quiz here, right? I'm going to give you 4 options for which of these statements most accurately defines a p-value. And then we'll get like a picture of that. Don't be afraid about being wrong with this, right? Because a lot of people are wrong on this question, right? So the first option is the p-value is the probability that the null hypothesis is true. Or it's the probability that the null hypothesis is true given that we observed this data. Is it the probability that we observe this data given that the null hypothesis is true? Or is it the probability that we observe this data, right? So have a look at those 4 options. And then it'll be interesting to get a point of view on, like, you know, things, which one do you think is the most accurate definition of p-value? Maybe Stella, I don't know if anybody's popping up letters in the chat, but it would be good to see if any of our online participants are giving a point of view on this. So how many people, quick show of hands, how many people think it's N? Okay, how many people think it's B? So we've got a few people saying it's B, right? How many people think it's C? Got a few people, but another same number saying it's C. How many people think it's D? Well, I'm glad nobody picked A or D because those were strong descriptors, right? But the answer is that that p-value, the best description of a p-value is actually C. Okay, and this is what makes it weird, right? Because if you look at it, you think that what we really want is the probability that our hypothesis is true. Given that we observe this data, that seems like the most natural thing we want to ask for, right? That's not what a p-value tells us. A p-value tells us what is the probability that you would observe this data, given that your null hypothesis is true. So intuitively, it's a bit back to front. And that is what makes the statistics that we learn in college quite difficult to absorb. I think a lot of people have problems with understanding p-values, because we're starting from a point that's quite back to front, from a kind of epistemological or I guess, you know, intuitive perspective. The good news is there are ways of getting big, right? And that's what we're going to talk about today. There are ways of getting a more intuitive way of expressing this, which is I have a set of data I'm looking at. What is the probability that my hypothesis is true, given that this is my data? Seems like a more natural way of looking, right? And the answer to that is Bayes' theorem, right? How many people, quick show of hands, how many people have heard of Bayes' theorem before? Quite a number of people. So Bayes' theorem is actually taught in high school in a lot of situations, right? But it's rarely brought into the realms of like modeling statistics until, you know, it would be unusual if you were on a you know, at college that you would do this before graduate studies. Normally they teach you classical statistics before that point. And so Bayes' theorem gives us that opportunity to flip how we describe, you know, that meaning of a p-value, right? So instead of asking the probability of the data given the hypothesis, we can actually ask what is the probability of the hypothesis given the data. And this is the formula for Bayes' theorem, right? Basically, you can get your probability of the hypothesis given the data by using the probability of the data given the hypothesis, right? So I'll look at this formula a little bit later, but part of understanding Bayesian statistics is realizing that it all comes from this quite simple formula. I think a lot of people think it's super, super complex, and it is complex. There are elements of complexity around it, which I'll describe later. But fundamentally, everything related to Bayesian statistics comes out of this very simple formula, right? So to illustrate this, I've set up a quick experiment, right? So imagine we have 2 dice, okay? One dice is blue. It has 6 faces, numbers 1 to 6 on each of the faces. It's a normal time, okay? It's what we deal with every day. Now the other die is red, and it has the numbers 1, 2, 3, and then 6, 6, 6 on faces, right? It's what we call a loaded die. The other thing is that the red die, the loaded die, is also heavier. Okay, so if we throw it up in the air, it's 2/3 more likely to land first compared to the other die. And we're looking at the game where we throw both die up in the air and we take the number of the die that lands first. Okay. And the question that I'm asking is, if the first die to land shows 6, what is the probability that it was a loaded red? Okay. So what we're asking is, what is the probability that it's red, given that it landed on 6? Okay. But do you think that probability would be low, moderate, high? High. You'd expect it to be high, right? Because everything is pointing towards this die landing first, and for 6 to be. So it's not going to be 50-50, right? So for those of you who have anything open on your phone, there is a, if you can pull your phones out, play this game, okay, you need to go to dicegame.keithmcnulty.org. If you can click on that, and we have this little game, okay? Now what you can do, I'll give us about 2 minutes to do this, right? But you can either like keep rolling the dice yourself, putting will record for you whenever a 6 comes up and whenever that's a red 6, okay? Or you can just put in 2 minutes and click start the game, and it will just repeat the throws for you for a couple of minutes. So let's actually go ahead and do that. You can click in number 2 under minutes, Stella. And
Number 2.
where's the minutes there? Just click on 2 minutes. Yeah. And then click start the game. And then you'll start to see it's going to just I programmed it in the background to have all these, 2/3 chance of the red landing different faces. And over the next 2 minutes, it's going to just keep throwing. And I'm interested in how many 6s were red 6s, right? That will give me my probability that it was the red die, given that it's a 6. And we'll see what that comes up with. And if you guys are playing the game too, we'll kind of get a quick show of hands about what number of people come up with. So far it's at 100%. Still at 100%. And by the way, we were talking about AI earlier before the session started. I coded this entire application in AI in 2 minutes. So we're not at 100% anymore. And really the whole purpose of this game is to say, okay, there's a theoretical formula for probability, but in the end, when you run experiments, some will land them closer, some may not. And what we're looking to see if like the real life numbers actually mimic what Bayes' theorem would tell us. Stay where you're there. Okay, just scroll it up a bit if you can. So I'm getting 92.9%. That's the probability that the dice was red, given it 36, right? Has anyone else finished the game? What have you got?
76.2.
We got 76.2, so we got 92, we got 76. Anyone else? You got 100? Okay. What else do we get? 86. 86. 2.92. Fantastic. And 93.
75.
75. Okay, maybe 9. Anything popping up on the chat still there, or is anything not that I'm seeing this thing? So from the numbers I've heard, I probably zone in on what Jeremy said as an average, right? Which is I think 86. That's what Jeremy said. So if we go back to the presentation and click on. So now let's see what happens when we actually put numbers into Bayes' theorem, right? So the probability that it's 6 given it's red, well there's 3 sides are 6 on the red, so it's a half. Probability that it's red, we already know is 2/3. Probability it's going to land on red. We can also calculate probability in 6 by just doing the weighted probabilities of whether it's red or blue, which gets us 7/18, and then we plug all that into Bayes' theorem to get the problem that it's red, probability that it's red given the 6. We get 6/7, which is about 86%. Right, so Jeremy gets a special promise. But you can see that, it's Bayes' theorem is probably right. Okay? It's landing on the right average there. So Bayes' theorem is real, it's helpful, and it is actually the foundation for how the types of modeling that I'm going to show you there. So how do we actually apply Bayes' theorem, in this type of context, right? So let's imagine that we're introducing a new learning program for engineers in our country. Okay, and this learning program, the purpose of it is they're teaching them to pass a certification test. And because we've only just introduced it, we don't really know what pass rate we can expect, like how effective the learning program is. But we do know a few things, right? We've spoken to the experts who designed the program, and they've constructed the program. They think that the pass rate will be between 80 and 90%. They're not 100% sure of it, right? So they think there'll be some variability around. They think 80 to 90%. And we have a small pilot group of 20 engineers who have completed the program and taken the test, and 12 of them passed. So here we have what's called our prior belief. And here we have some data. Now what we want to do is calculate an updated belief based on the prior belief and the data that we have. We want to put those together. So this is what I was talking about, injecting knowledge and expertise into how we model. Right, so let's think about it. So Bayesian statistics is all about simulation. So what you're doing is you're taking all your rows of data and you're applying Bayes' theorem to each one of them, right? So one of the reasons why people haven't used Bayesian statistics a lot in the past is because doing that type of simulation is computationally expensive. And up until maybe 10 years ago, the average person didn't have the computation power to do a lot of Bayesian statistics, right? But nowadays it's pretty much freely available. It's rare that your computer will crash when you're trying to run a Bayesian model, right? But let's call the pass rate, the proportion of people that think will pass the exam. Let's call that beta, right? Now what we're going to do is we're going to take 1,000 possible values that beta can take. So we know it's a proportion or a probability. So it's going to take values between 0 and 1. Okay. So now what I'm going to do is I'm just going to take 1,000 values between 0 and 1. Okay. That's the list. So this is what I'm doing with this piece of code. Is I'm creating a list that's 1,000 values long, and they're all incrementally between 0 and 1. So these are just a whole bunch of possibilities for what my pass rate could be. And then I'm saying, okay, now our experts said that there would be somewhere between an 80 or 90% pass rate. Okay. So I need to create a statistical distribution that looks a bit like that, where it's most likely to be between 80 and 90%. And the distribution to use for that is to use Bayesian statistics. You have to know your distributions quite well. But the beta distribution is designed to produce a value between 0 and 1. And you create it based on your expected number of positives and your expected number of negatives, right? So here I'm saying I expect a beta distribution where most likely I have 8 positive results and 2 negative results. That's around the 80 to 90% mark. So with this piece of code, all I'm doing is simulating that distribution. So that distribution will tell me that each of these values has a certain probability of occurring. So obviously, if it's 86%, it's going to be quite a high probability of that occurring. But if it's like 3%, it's going to be quite low probability of occurring. So that will just simulate that for me. So if we look at the next chart, we'll see what that simulation produces, right? So this is the visualization of our prior belief, right? It tells us along here we have all the possible values of theta from anywhere between a 0% pass rate and 100% pass rate. And here we have the likelihood of those occurring. And this kind of looks like what our experts have told us, right? It's most likely to be between 80 and 90%. So that's what we call our prior belief, right? We express it as a statistical distribution. Thanks. But we have some data, right? And the data we observed is that 12 out of 20 people actually pass. So what we can say is, what is the probability that that will happen for the different values of theta? right? So if like this is 100%, we're expecting 100% pass rate, then it's quite unlikely that we'll get 12 out of 20 passing, right? Similarly, if we're expecting a 0% pass rate, it's quite unlikely we'll get 12 people out of 20 passing, right? So in this line of code, I'm creating what's called a likelihood function. I'm basically saying, what is the probability that we would get 12 people passing out of 20 if the value of our pass rate is, all of those 1,000 different numbers, right? So creating another 1,000 data points that tell us our likelihood function. So by doing that, and I'll show you like what the output looks like in a second. But now we have two things, right? We have the probability, our prior probability of a certain pass rate. We also have associated with that, what's the likelihood that our data would occur if it was that pass rate? And those are the two foundational parts of Bayes' theorem. So we've got pretty much everything we need to run Bayes' theorem for each of these 1,000 values, right? So if we click on. So now let's see what that data looks like, right? So in one column, we have all these incremental values of theta from 0 up to 1,000. I'm just showing the first 6 rows here, but 1,000, right? For each of them, we have a prior probability according to our experts of how likely they think that pass rate will occur. And of course, down in these low values, it's extremely low. And then for each of them, we have what's the likelihood that 12 out of 20 people would pass if this was our prior, if this was our pass rate. Again, you'd expect that to be very, very small on the low values, right? So this is our data. And the great thing about Bayes' theorem is to update your belief, right? To get your updated belief about pass rate. All you really have to do is multiply the prior by the likelihood, and then add them all up and divide each by the sum of everything. And that gives you your new likelihood, your new probability that incorporates both the expert data, the expert opinion, and the new data. If we go to the next page. Right, so what we want is what's the probability of our pass rate? What's our pass rate look like now that we have the data? And we already have these two values in our previous spreadsheet, so we just need to multiply them together. And this thing will be divided by simply the sum of all those values. So that's what I'm doing here. I'm just basically multiplying those two values together, and then I'm dividing the whole thing, each of them by the sum of everything. And that gives me what we call our posterior. So what's our probability after we incorporate the data? So let's take a look at the next page. So now this is a view of our distribution of our likely pass rate once we've done that. Okay, so this one is the original prior, which we looked at previously. Now what we say is, having gone through that process with each row of our data, we come up with this new distribution, which says actually, if we put all this together, it looks like our actual likely pass rate is around somewhere between 0.65 and 0.7. That's what's most likely. So what we've said is, okay, thank you, experts. You've taken your data on board. We've also looked at what really happened. And based on only 20 data points, this is what your likely pass rate is looking like. Okay. So if we click on here now, it's this fantastic phrase in Bayesian statistics, right? Today's posterior is tomorrow's pro. Right? And this is a process called Bayesian updating. So let's imagine that we get data on another 30 engineers, maybe in a month's time. We've taken the program, 25 of them passed. Okay? We can go through this entire process again, except that our posterior probability, so the probability we landed with at the end of that pass process, we now use as our prior for the next process. We add our things in and we update again. So if you look at this here, what I've got, this is our original, our first prior that we had in the very beginning. This is what it moved to after our first set of data. And after our second set of data, you see this is our prior. We get to this new posterior here, which looks like it's something like 0.8, somewhere between 0.75 and 0.8. Now, the other thing you'll notice is that these curves of distribution curves are becoming more narrow as we add more data, which tells us that we're becoming more certain about what our result is. So instead of saying, okay, we're going to wait here until we have like 300 data points in 2 years and then run like a class 6 statistical analysis, we can actually use Bayesian inference to say, let's just take data in batches as it comes in, and let's continuously update what our belief is on the basis of those batches. So it's extremely powerful from that point of view, right? Click on. Okay, so what does that mean if you're running a regression model, right? So what you saw there is you express your beliefs in Bayesian statistics or statistical distributions, right? So you say, my prior belief is this distribution. I'm getting the following data. My new posterior belief is this new distribution. And it's the same with running regression models. So let's look at how, and those of you who've kind of looked at my book or done like linear modeling, nor like regular linear modeling, will be familiar with some of this code. But let's go back to our, UG test data, that data on the biology degree program, the scores that people have. And remember now we've cut it down, we only have 20 random students in our data set. And let's say we want to understand the relationship between the first 3-year scores and the final year score. So the final year scores are outcome variable, and year 1, year 2, and year 3 are input variables into the model. And when we do linear regression, we're asking like, how much does a point increase in each of those input variables affect the outcome variable, assuming like none of the others change. So I'm running this simple linear model in R, no like Bayesian fancy stuff here, just a regular linear model. And it's telling me that these are the likely coefficients of my model to 95%. These are the 95% confidence intervals. And they're extremely wide, right? So year 1 can be anything between a reduction in points of 0.19 all the way up to an increase of 1.08 points. Similarly, year 2 has a wide range of effects. Year 3 is a wide range of effects. So we see this problem I described earlier of your inference has been very, very wide because you only have a very small number of data points. Now, you can't stop that from happening, but with Bayesian statistics, you can describe it's better, right? And you can introduce prior knowledge into your model. So if we look up to the next slide, okay, let's take a Bayesian approach to running that model, right? So that allows us first of all to incorporate expert knowledge. So let's say we go to our experts and they say, we do not believe that the year 1 score has any influence at all on the final year score. And let's say like we want to take that into account in our model. So this allows us to do something which we can't do with traditional regression mostly, which is to control the coefficients, right? So here what I'm doing here now, the package that you would use if you're an R programmer, and in the book I show them do this in R and Python, but in an R programmer package you would use to run I'm starting Bayesian models called BRMS. And the first thing you would do is if you can ask, the model, you can ask R to run these models without any prompts, right? It will basically have like really, really wide priors to assume no kind of prior knowledge, kind of like running a regular regression model. But you can also give it specific priors and say, this is what we believe our kind of prior, this is our prior opinion on some of these things. So here I'm taking what the expert has said, and I'm turning that into a statistical prior distribution. So I'm saying, okay, for my year 1 coefficient, I want to set it at a normal distribution with a mean of 0 and a standard deviation of 0.05, which basically means an incredibly narrow distribution that doesn't move away from 0 very much. So that's me kind of saying I'm trying to force my coefficient to be 0 here in my model. So I'm setting that prior. And now I'm running my Bayesian linear regression model, which is BRM. It uses a lot of the same syntax as a regular regression model, but you see a lot of these, and here you see I'm putting my priors into the model, which I've defined previously, right? To make sure that it takes on board those. And then I have a bunch of things that are very specific to Bayesian modeling, right? But because you're simulating in Bayesian modeling, you're running thousands of simulations. You have to like give it some instruction, right? So I've told it to run like 4,000 iterations, which it would do in maybe that code will take maybe a minute to run on my machine. Now you can tell it to do like 100,000 iterations, but we're probably still here tomorrow morning if you did that. But simulation is a big part of Bayesian statistics, which is why like a lot of people get shy away from it, because it can be computationally intensive. And now I'm looking at what it tells me about my coefficients now. And now, if you look at year 1, it is taken on board by prior, because you can see that if you look at the what we call the granular, the different term, it sits between minus 0.86 and plus 0.1. So you have like, it's basically averaging out around 0, which is what we wanted it to do. And then the year 2 and year 3 coefficients have adjusted to take into account that we're kind of pushing that prior on the model. So what we're basically saying is if we're taking our expert's opinion seriously, this tells us that the year 2 and year 3 coefficients will have something like these values, right? So that's the first value of the linear regression. The important thing to take back out of this is that everything that comes out of a Bayesian model is expressed in terms of a distribution of some form. So whereas for a traditional model, it'll be expressed in terms of a mean and confidence interval, here will be, you can get an entire distribution for each of your coefficients. So if we look to the next slide, you can actually visualize the distribution of your coefficients with a Bayesian model, right? So here I'm basically using a plotting function to tell me right now, based on running that model, what does the distribution of my coefficients look like? And it shows that our year 1 coefficient, as we required, as we've said, it's actually quite narrow and most like and centered around 0, which is how we set it in the prior. So that's behaving the way we want it to. But our year 2 is actually very, there's a lot of possibility for year 2. So it's not clear, but what we do know is the vast majority of that distribution is greater than 0. So we can state to some degree that there's a high likelihood that year 2 has a positive effect on final scores. And then for year 3, we see like a better and more defined distribution and actually quite, strong value on it. So we can say year 3 scores have a very, very, comparatively strong effect on final year score. So what you often see in Bayesian statistics are people are not expressing their coefficients in terms of numbers. They're expressing them in terms of images like this, distributions of possible values. And that has a couple of very good side effects. If we click onwards. That then allows us to make really precise statements about our coefficients. So one of the challenges with a confidence interval, which you learn in traditional statistics, right, is that's about frequency, right? So when you describe a confidence interval, what you're saying is, if I ran this model multiple times, 95% of those times, this number would land between these two values. So it's a frequency count. It's not an actual statistical distribution. It's not giving you explicit probabilities, right? But Bayes modeling gives you explicit probabilities, which means that through your simulation, you can ask really, really specific questions about your coefficients. So here, for example, I might ask, okay, what is the probability that year 2 performance has a positive effect? So let's say, it gives you a wide distribution where you want to be able to say to your, stakeholder, here's the likelihood that it actually has a positive effect. And what I'm doing here is I'm simply running my samples. I'm saying, take a whole bunch of samples of my coefficients and count how many of them, or average how many of them are greater than 0. And the answer I get is like 95.5% of the coefficients that we've simulated are greater than 0. So you can go back to your line and say, there's a greater than 95% probability that this particular year scores has a positive effect. Fun year, and that's quite compelling, right? To be able to give that precision. But it also means that you can ask quite advanced questions that you would not be able to give it to a traditional regression model. So imagine somebody said, what's the probability that year 3 performance has 3 times the effect of year 2 performance on that final score, right? So what I'm doing there is I'm taking a whole bunch of samples again of my coefficients, and I'm saying, in how many of those samples was year 3 greater than 3 times year 2? And it says that happens in 54.8% of occurrences. So you can say there's basically a 55% probability that your year 3 score is 3 times as influential compared to your year 2 score. Now, there are ways of getting like traditional regression models to do things from that, but it's not easy. Whereas with Bayesian statistics, you're able to ask a lot of these really quite advanced questions quite naturally. Great. So that is really important. That was the main components of my demonstration. So the main takeaways that I'd love you guys to have is, it is worth considering Bayesian inference. It's a little bit more of like a learning investment up front, some more computational demand. It's a little bit more finicky to run these models compared to traditional models, but once you're done, once you're able to do it, all the time. And the main reason to consider when you're working with small data is the two big advantages. One is you can actually mathematically pull expert knowledge into your model, as long as you can express that expert knowledge as a statistical distribution of some form. And that's what your prior is. And then the second thing is it allows you to play around with your probability estimates, so you can give really precise answers to questions, which are much more difficult to do with like a free-breakfast model. We'll just click on or if I have anything else there. Oh yeah. So in the new version of the book, it contains all the stuff that the previous book contains. Chapters 3 to 11 teaches you all the classical methods, right? So if you're coming to a talk like this, coming across this is the first time you've even come across a regression model in any degree. If you're working through the book, you definitely need to start with those chapters, right? It would not be jumping into Bayesian regression first. Then once we get to chapter 12, what I do there is I basically discuss what is Bayesian inference, how does this work. So a lot of the very early slides I showed you here, I'll go into a bit more detail on that. Like how does Bayes' theorem actually, help us to bring in prior data, get our posterior distributions. And then in typical style for the previous chapters, I use chapter 13 to basically go into detail on here's how we run a linear regression using Bayesian approach. And then in chapter 14, it's basically a list of all the other types of models and, how would you run those models in a Bayesian approach. And then the last chapter, chapter 15, which, I may do a talk on in the future, but this introduces something, which is quite modern to do, but a really, really interesting field, which is related to Bayesian statistics, but it's called causal inference, right? And this field looks at, when you're running a model, like it'll tell you how different variables are associated with your outcome, but it doesn't really tell you if there's a causal effect. One thing causes another. Now, it's usually completely impossible to be able to say that with certainty, but one of the things you can do if you're really disciplined is you can think about, okay, is there evidence of a possible causal effect? And the way you do that is by being very careful about which input variables you choose to put in the model. If you're looking to determine if there's evidence of potential causal effect of a certain variable, it may be that you have to only put that variable in the model with no other input variables, or it may be that you have to add one or two specific input variables to eliminate other possibilities of effect. So that whole chapter at the end, which I left to the end because you kind of need to know the other stuff to get there, is like, to some extent, the holy grail of where a practitioner should be going, right? Which is, as well as being able to run models, to actually have good knowledge of how to construct them well, if your purpose is to tell your stakeholder these things, that there's evidence that actual cause and effect. There's a lot of association between variables are actually not causal, right? They happen because of all the things that are going on. So that helps you navigate the book if you're picking up the new version. I think that's it. I think I've already thrown far too much statistics at you for an evening, but I'm happy to take it if you guys have any questions, and also if you just want socialize for this, that's fine also. But yeah.
Is there a relationship between your causal modeling with Bayesian and structural equation modeling?
Could you repeat the question so people?
Thanks for reminding me. Yeah, so I think the question mark I was, is there a relationship between the causal modeling that I mentioned towards the end and structural equation modeling? The best answer I give is not really. So structural equation modeling is really just a way of dealing with latent hierarchy of data. So you might have a lot of data points, and throwing like maybe you have 15 data points in your observation, right? But those 15 data points actually might have a latent hierarchy. Like 5 of them might relate to a certain construct, 2 might relate to another, 7 might relate to a third, and that it's more valuable to your stakeholders to see that model written in the kind of the high level constructs rather than the 15 items, right? That's what structural equation modeling is for, right? It helps you articulate an invisible or latent hierarchy in your data, how it applies to your model. Whereas causal modeling is really about isolating the causal effect. So when you run a structural equation modeling, unless you follow causal inference principles, it would not necessarily give you causal effect. It will just give you relationships between your data. But you need to actually use causal techniques to get out of the data. There's evidence for causal.
So if the expert knowledge is giving you a range of potential scores, why go with a lower limit rather than range or get like, up or down, up or down? To make sense.
Sorry, that question was, if the expert knowledge is giving you a range, why would you go with a particular part of that range? Is that what
Yes.
the question is? I mean, so one big question that comes up in Bayesian statistics, I think, is how you select your priors, right? And there are two types of priors in Bayesian statistics, right? There's what we call an uninformative prior, which basically means your experts have no idea, right? And so what you'll do is you'll take a uniform distribution of all the possible values, if you think, with no variability of any particular part of the scale, and you'll run it on the basis of that. And to all intents and purposes, you might as well run a traditional regression model if that's what you're doing. But some people just like to have some of the flexibility that Bayesian gives you. So they'll run it with an uninformed prior. And then you have what's called an informed prior. Now, for an informed prior to be valuable, it needs to point to a certain range of values that are highly likely, right? So there needs to be a good basis for making that choice. And that's really, and your distribution then takes care of that. If your distribution is telling you most likely your value is like 3/4 way up this scale, then the model will then apply that and take it into consideration. So really the question is, do you go with what we call a completely flat prior, uninformed prior, or are you actually taking a point of view on where the other values are? So
I'm just wondering, and I think you might have given us the reasons, but did you ever consider bootstrapping the data and running a traditional model?
yeah, so that's really good. It's a good question. So the question was, what I consider bootstrapping the data. Some people may know what bootstrapping is, or some people may not know what bootstrapping is. But bootstrapping is really an attempt to do Bayesian statistics without doing Bayesian statistics. That's the best way I think to describe it. It's basically what it's saying is, okay, well, your traditional linear model, your frequentist model, is telling you that there's, certain, your coefficients are going to be between these values, some probability, usually normal distribution, and if it's a linear model. And basically what you're saying, okay, I'm going to simulate all of that. Okay, and I'm going to use that to play around with my model, right? So it's kind of doing the Bayesian thing, but it's doing it using a frequentist foundation. You'll get pretty much similar answers, right? But it's kind of difficult to set priors in that. That's the only thing. It's more challenging to set priors. But if you ever hear the term bootstrapping coming up, what they're doing is they're basically simulating off a frequentist model, right? It's in very similar principles.
I guess it's kind of esoteric, but like, to what extent do you trust your experts? Like, what you're trying to do? Like, how do you make decisions about that? Do you compare the original model to the expert prediction?
So there's something in Bayesian statistics that's called, that's the question. Apologies. So a really good question is like, how do you trust your experts? Is there any way of like being sure or verifying that your expert opinion has some weight or value? And it's not just some random person giving you an opinion that doesn't have it. There's something in Bayesian statistics called your prior being overwhelmed. And what that means is when you get enough data, the pattern starts to take the form of what would have looked like if you were just using the data element, right? So eventually, for example, we get 20, 30 additional data points. They can get another 50 after a while. Eventually, you get to a point where if your prior is really wrong, the model will just completely ignore it. And basically, you'll get the equivalent of like a traditional model just on the data, right? And that's called your prior. Some people call it your prior being swamped. Some people call it your prior being overwhelmed. But that's probably the best way of validating. So my view is if you're operating on small data, there's no harm in putting your expert's opinion in. using your Bayesian updating process. And over time, if your expert's opinion is completely wrong, the data will you know, reflect the reality of the data that's coming in. So, yeah. Jared.
So there's a big trend, this is kind of a bootstrapping thought. My mind put this synthetic data versus Bayesian off of central experts data. Is it, would your opinion be the same as bootstrapping to synthetic, or do you see a nuance between the two?
Yeah, my main exposure is, sorry, I've tested. So the question was, to what extent is synthetic data, is the question of synthetic data similar to the question of bootstrapping, basically, and how does that compare to Bayesian? But my main exposure to synthetic data is you're creating it because you don't have any, right? And, you know, it's, once you have your synthetic data, you run your model on it, you choose it to be like a, you know, a traditional model or a Bayesian model, and then bootstrap it. But the fact is that you're going through a process based on fictitious data, right? And so you're not going to draw any kind of active conclusions from it or drawing decision making like that. The main reason why we have synthetic data, right, is because we're teaching. That's often we have synthetic data because we're teaching. We don't really have a real data set we teach on, so we'll create data that mimics the properties of a real data set. Or we're doing it. You know, what will happen in some circumstances is like at work, I know that I'm going to have to run a process in a month's time, and the data won't come in until 2 days before, but I have to give it a really quick turnaround. And so I want to be able to test it beforehand before I get the data in. So I'll kind of create a synthetic data set that looks like the data that I expect, and then I'll run it, right? But I wouldn't kind of apply questions of the validity of the model because it's synthetic data, right? You wouldn't do anything with results. Any other questions, or people want to wrap it up? Sounds like we're done. Sounds like we're done. Jeremy, do you want to wrap it up?
First, for you having concentration, because I know you had a full day of work as well, and for everyone else, you showed up. It's gorgeous outside. What's wrong with you? But you're here talking about Bayesian mathematics on people analytics, and it's fantastic. Like offline, socialize, talk about this, where you can see it. No, so I do want to ask about silver later, but this will not be something for right now, because it takes up a great Bayesian on full predictions. So to wrap up, we do have room for a few more minutes. Please do socialize. One of the things, if you've not tuned with us before, is if you are looking for a new role, or if you're looking to recruit, we always have one part of the space that we designate as kind of that corner. We'll call it that corner over there. That I'm on there, but I'm online, so just walk to the other part of the so we can talk to us as well. We will be having some more programs for the remainder of the year. We're still kind of planning out those areas, and thank you to Cynthia under this fantastic project. This is, by the way, a photography studio. As you can see, all this art is the photographer. Very, very cool. Thank you online and in person, and we will see you soon. Thanks for listening. Now you're